but we will do select sections from it, 2 this week at least, and 2 when we get back from Thanksgiving, or hopefully I'll just go ahead and put them up this weekend and you can get them done as you can. So we're going to start using integrals in space and see what we can make from that. All right. I am using a new software here, so bear with me because the upgrade on my computer that enabled me to get back online does not let me use some of the software I had before. So here we go. Double and iterated integrals over rectangles. So double integrals is what we're going to start with, and we'll discuss what iterated integrals are in a moment. So here's what we're starting with. Just want you to remember what you learned when you learned how to calculate single variable integrals. And you were taking a curve like f of x here, and you were calculating the area underneath the curve over an interval from a to b. So it was always the area between the x-axis and the curve f of x. And of course, here's the integral symbol that means the same thing. And so we're going to expand this like we have in every other situation, going from single variable to multivariable, we're adding a dimension. So when you add a dimension to area, you get volume. And here we have a picture of the xy plane. And so instead of integrating over a range from a to b on the x-axis alone, we have got a plane that we've divided up. We've partitioned it, is the word, into rectangles of varying sizes. And so they've isolated one little rectangle here. They've shown you that one horizontal length is delta x, and then they use a k for our subtitle is the word I'm looking for, subscript, thank you very much. And then the height of the rectangle is delta yk, and the k is just talking about the number of rectangles in the partition, okay? So when we identify a single point in that partition, we call it xk, yk, and when you multiply delta x times delta y, you get delta a. And that is one of the partitions inside this domain, as it were, this region called R here. And so we're always going to keep in mind that these are rectangles in this section. We'll limit ourselves to rectangles. So the change in area equals the change in the horizontal coordinate times the change in the vertical coordinate. And that's the basis for our single unit here. Now, if you recall in single variable, we did delta x, okay, so dx is what that turned into when we took the limit. And if you'll recall the Riemannian sum where we took dx of a certain width, and then we took the limit as dx headed to 0. And so we're going to do the same thing for a volume expression over here. Let me, okay. So here's how I have to flip slides now. So I'm going a very brief description of the derivation of the integral here. S stands for the Riemannian sum of n partitions, okay? So, or little rectangles. And so I told you k was the number of a rectangle, and so there are n rectangles, and k goes from 1 to n. And this is the sum of a value of the function at this particular point times delta A, so the change in area. Now, to turn this into volume, we're going to take the limit as n goes to infinity. So the partitions are getting smaller and smaller and smaller, and we're adding up those areas. The double integral indicates that we've got the delta, the dA is two-dimensional, so we've got two integrals. So I want you to realize this is f of xy is a z value. It's a height. So if you'll notice here, this blue dot is the height of this rectangular column here. So we've got the change in area as dx dy times the height gives you a piece of the volume underneath this green curve, but sitting on top of the xy plane. So it's three-dimensional, and the area provides two of the dimensions, and the f of xy term gives you the height of that column, so that turns it into area times height, which would be volume. And we're adding them all up, that's the S, and then we're letting the number of partitions go to infinity. So they're getting smaller and smaller and smaller. And where as the area of each little partition goes to 0 and goes to infinity. So we're getting infinitesimally small chunks of volume and adding them all together. It's very similar to the idea of single variable calculus. All right, so here's some pictures as the chunks of area as delta A goes to 0. So here they are, rather large chunks where the rectangular partitions are large. They get smaller here when we have 64 of them. If we have 256 of them, they get even smaller, and you can see how it more accurately approximates the area under the surface as the partitions get smaller. So that was a good illustration in the book. So here we go. We've got a theorem to deal with. Fubini's theorem. Not really familiar with who Fubini was, but his theorem is very nice, and we'll use it in this section a bit to make some things easier on us. And the conditions are that we have a function f of xy, which is a surface, that is continuous throughout the rectangular region that we'll be integrating over. Okay, so they call the boundaries of x a to b and the boundaries of y c to d. And so the double integral over the region R of f of xy dA is. So we pick our two integral symbols, and notice how they put AB on the inside, that's our x limits, and CD on the outside, that's our y limits. And then they put our function as the argument of the integral, and then our differentials. So since the AB limits for x were on the inside, that dx is on the inside, we'll be evaluating this integral first. And then, once we've evaluated the inside integral, then we'll evaluate the outside integral with respect to y. Now, this theorem is telling you if you flip the order of integration, you put the x limits on the outside and the dx on the outside, then they're in a different position than they were, and then CD, those are the limits of the y variable, and dy, that's the inside integral now. So you can almost put parentheses or brackets around the inside integral. And I like the illustrations below because they help you understand the literal difference in what you're doing here. The theorem says that the order of integration does not matter. And this is over a rectangular region, by the way, very specifically a rectangular region. We'll talk about when we switch to different shaped regions, how this idea is affected. But here we are on the left-hand side. They have this line parallel to the y-axis. All right, so we've got our function z equals 4 minus x minus y, which is just a plane. And we want the volume underneath it as y here goes from 0 to 1, and as x goes from 0 to 2. So they've set this integral up, a, based on x as an independent variable, is going to be, here's our function, f of xy. And since we're moving in a direction parallel as y goes from 0 to 1, see the bottom limit is 0, the top limit is 1, this is our differential in the y direction. All right, now if we wanted to do, so that's going to give you the area of this blue piece right here. And then we're going to need to find the volume generated as this piece moves from x equals 0 to x equals 2, and that would be the outside integral. So that's one way to define it. The other way to start off defining it, that inside integral, is for the line to be parallel to the x-axis instead of the y-axis. So we'll have dx for a differential underneath our function 4 minus x minus y, and our limits are x equals 0 to x equals 2. So these are pictures of what you're doing. You're finding the area of this piece, and then integrating it again moves it from y equals 0 to 1, giving you a volume. All right, so that's what we're doing when we're doing iterated integrals. So the word iterate means to repeat. So we're doing more than one integral, and so I wanted you to see a picture of this function that we're about to integrate the area under this green surface, 100 minus 6x squared y, and we're going to integrate from y equals negative 1 to positive 1, and from x equals 0 to 2. So this is the picture, and the double integral indicated here over the region R of f of x, y, dA gives the volume underneath this surface over the rectangular region R in the xy plane. So this is a picture of what we're about to do. All right, and here it is. So I'm going to walk you through what it is to do a multiple integral here. Okay, so I want you to pay attention that I'm going to be pretty much sticklerish about you showing the work properly here. And so when we do two integrals, okay, notice they didn't tell us whether we should put dx or dy first. And since they're equal, it doesn't matter which order we do them first, technically speaking. I will say sometimes it's easier to do one order over the other. So if you set it up in one way and try to do one and it's too hard, then maybe swap them and try the other way. And you'll see what I mean, perhaps, in a couple of the homework problems for this section. But I'm going to put my f of xy here. And so I will say the book tends to default to dy dx a lot. It doesn't mean it has to be that way or that it's the only way to do it, but I just want to draw your attention to what I'm really doing here the first time you walk through this. So I could do dy dx, I could do dx dy. It really doesn't matter, especially with a polynomial type function here. It's not going to be hard either way, but since dy is on the inside, I want the y limits on the inside integral from -1 to 1, and then the x limits from 0 to 2. Okay, now I could have just as easily set this integral up this way and done, here's my f of xy. I could have just as easily done dx dy, which means x is on the inside, so these are our limits on the inside, and these are our limits on the outside. So both of these would give you the same thing. I don't particularly have a reason to believe that one is any easier than the other, so I'm just going to proceed with the one on the left. Okay, so we're going to bring this down, and when I say proper form, I mean we're not using this integral yet, but it has to be in this step. So I'm going to integrate this inside integral, and I'm going to leave it in the sandwich that has the integral symbol on one side and the dx on the other. Those have to stay in this step because I'm not using them yet. Okay, please don't do shortcuts where you leave it off and then happen to remember later in the problem to slap it back on there. Okay, I don't like you to skip steps in that fashion because it does not communicate clearly to me that you know what you're doing. And that is your job, to communicate to me that you know what you're doing by showing the work I need you to show. So how do I integrate 100 with respect to y? Well, that's going to be 100y, the derivative, or excuse me, the integral of a constant. Okay, and then here's the trick to this. We're integrating with respect to y, which means x is a constant, and we will hold it constant. So not just -6 is a constant, but x squared is a constant, and we will integrate y. Now using the power rule, the integral of y dy, if you recall, is y squared over 2. So I'll put my y squared, and we'll put this over 2, and that will be evaluated. So now we have to do our limits from -1 to +1. Okay, now I happen to like to go ahead and clear those. Oh, I just got rid, that's odd. It won't let me just undo one little thing. Interesting. Clear markers. There we go. So it still doesn't like to let go of just the markers and not the rest of the problem. Okay, so I am going to just make sure this was -6 over 2, so that's going to be -3 here. Okay, still getting used to my website. So that's a -3. I'm sorry if it's not clear. Okay, so I have to bring down my dx. So this sandwich of the integral and the differential have to be on the outside yet. I haven't used those. But I need to evaluate this last integral I've just taken from -1 to +1. So that's going to be, all right, here's part of my answer, 0 to 2. And then substituting in 1 for y, not for x, just for y, we're going to have 100. And then substituting in 1 for y here, we're going to have -3x squared. And then we've got to subtract. Substituting in our lower limit, -1 times 100 is -100. And then -1 squared is +1 minus 3x squared. All right, and all of that we need to clean up, and we don't need to forget our dx. Okay, So we've got minus negatives makes plus, and so minus 3x squared plus 3x squared, those go away. And we have 100 plus 100. So now we've simplified this down to the integral from 0 to 2 of 200, let me fix that, 200 dx. All right, so the integral of a constant, oops, I'm actually taking the integral now, so 200x, not y, pardon me, and we will evaluate that. It doesn't matter to me whether you use brackets or parentheses when you go to evaluate, as long as you put the limits at top and bottom, okay? And so when we substitute in 2, we get 2 times 200 minus 0 times 200, and the value of our integral is 200. All right, so you see how we simply do the inside integral, simplify it completely, and do the outside integral with what remains. That is how you do a double integral. So the secret is to make sure that you hold the variable constant that you are not focusing on. So we had to focus on the inside integral first. That was with respect to y, so x was held constant. That is the key. All right. So here is our next sample problem. So here we have a surface, and we want to calculate the double integral over the region R of f of x, y, dA. So here we are, x goes from 0 to 1, y goes from 0 to 2, and here's our rectangular region. So the volume of this solid with the curved top here. That's what we're going after in the next problem. So here we go. And in worded form, find the volume of the region bounded above by the elliptical paraboloid here and below across this region from 0 to 1 for x and 0 to 2 for y. So two integrals, and I'll go ahead and put my function in. Again, this is a polynomial type function, so the order of integration really doesn't matter that much. I'll do dx first and then dy on this one. I will say sometimes it's easier to flip it, okay? So that's going to be something you learn by doing, and in the homework you'll have the choice to set some of them up the way that you choose. And if you find yourself getting bogged down in a calculation that's too ugly, or frankly you don't know how to integrate at all, I want you to switch the order of integration and do them the other way around. Okay, so I've got to focus on my inside integral, this one, first, okay? And so we're going to say the integral of, with respect to x, of 10, okay, well, let's do my sandwich here. Okay, so that's going to be 10x. And the integral of x squared is going to be 1/3 x cubed, if you recall the power rule. And then this is a constant. If we're integrating with respect to x, then 3y squared is a constant. And so that would end up being 3xy squared. And we need to evaluate that from 0 to 1 for x. You always have to keep track of which variable you're taking your integral with respect to. So I'm going to do my limits substituting in for x. All right, so integral from 0 to 2, still working on that. And so every term has an x in it, so the bottom limit will only produce 0, so I only have to worry about the top limit. And if x is 1, then we've got 10 plus 1/3 plus 3y squared. And that is with respect to y. So now I can clean this up a little bit. From 0 to 2, 31/3 plus 3y squared with respect to y. All right, so the integral of 31/3 is 31/3 y, and the integral of 3y squared, I'm going to see, make that y cubed and bring the 3 down, and that is going to end up being plus y cubed. And I can integrate that, evaluate the limits from 0 to 2 here. Okay, and since both terms have a y, the bottom limit will be 0, so I just have to plug in the top. So I've got 31/3 times 2 plus 2 cubed is 8, so that's going to be 62/3 plus 24/3, and I really don't want decimals, 86/3. All right, If I want decimals, I will tell you how many decimal places I want. Otherwise, I'd like you to give me a reduced fraction. And yes, you are allowed to use a calculator if you care to. Um, there's not a whole lot of use for a calculator here, but arithmetic that does get rather involved is always a nice time saver on the calculator if you feel more comfortable doing that. All right, so that's pretty much it for the content in this section, but I wanted to remind you of saying some things you are going to need for this. These first two formulas are often in the back of the textbook. I just wanted to bring them up as I did all the questions in this section as practice that I put on the suggested problems list, and I needed these two formulas, which are in your book. I also needed this formula, which is very rarely included in any kind of integral formula list, but you could derive it yourself with integration by parts if you care to, or you could simply learn this one. I will remind you that integration by parts is something that you will use for our integrals in this homework assignment and some future things. And although I neglected to put it on the slide, you will sometimes benefit from integration by substitution. By U substitution, sometimes it's called. So make sure that these things that have come before are useful to you, and if we need to talk about them the next time we have a sync session, I'm happy to. Hey, I wanted to demonstrate integration by parts for you one time before I was finished here, just to give you a little refresher. And so I've got a very typical integral here where we have a product of two functions, and that is often a time when integration by parts is helpful. And so I remind you of the formula down here. We have to identify u and dv in a way that describes this expression up here. And so the first thing that occurs to me is to call ux, okay? And then we have to identify dv. Well, that would be the rest of the expression, cosine x dx. And I think a lot of people get stuck on integration by parts because they forget that dv has to have a differential in it. So to get du, we take the derivative of x, which is just dx. And to get v, we take the antiderivative of cosine x dx, and that's going to be sine x. So here's how we put this into the formula. This is going to be u times v, or x sine x, minus the integral of v du, and v is sine x, and du is dx. And so now we need to continue to evaluate this integral here, and this part comes down unchanged. All right, the antiderivative of sine is going to be negative cosine, and we would end up adding a c, since this is not a definite integral, so we just need to clean this up. X sine x plus cosine x plus a constant. All right, there's a demonstration of integration by parts.